Alright guys, so in this video we're going to talk about normality again, and this time I'm going to approach it in a different perspective. And the reason I'm doing this is because I'm kind of preempting the next type of question that you might see with normality types of problems. It doesn't have to necessarily go with acids and bases every single time. We said that's where we find normality the most. But normality can be applied to any type of compound, just like a concentration unit can be applied to any type of compound, right? We're not restricted to just acids and just bases. So in the previous video, I kind of discussed the relationship between normality and molarity. So normality and molarity. And we said that we basically look at the number of hydrogens, or in the terms of a base, the number of hydroxides, for the most part, not every single time, the number of hydroxides in a base. So for instance, a 2 molarity HCl solution would also be a 2 normality HCl solution because there's only one hydrogen for every one molecule, right? But we said a 2 molarity H2SO4 solution, well, we're not looking at the entire molecule for normality, we're only looking at the hydrogens that are here, and that's basically 2 times 2, which is 4 normality H2SO4. Now, there's another way to kind of do this on a sheet of paper using dimensional analysis for those of you who enjoy doing that type of thing. And the reason I'm presenting it this way again is because we will use it this way to solve some of these other types of problems that do not involve acids or bases, right? Sometimes people are more comfortable with this type of setup, and if so, I'm going to introduce it here. Okay, so the way that we would do this is, let's say that we've got 2 molarity HCl, right? Now 2 molarity basically means 2 moles per liter, right? So I can start my dimensional analysis off that way. So 2 moles of HCl per 1 liter of hydrochloric acid. That's the definition of molarity, moles per liter, right? So I just rewrote the dimensional analysis to make it fit the template. Well, mole of HCl on top, mole of HCl at the bottom, and then some people are going to look at this compound and say, okay, well, if that's mole of HCl, how many moles of H plus could I get from that molecule? Well, for every 1 molecule of HCl, I have 1 hydrogen. Well, there we go, 1 mole of H plus. We also call this an equivalent, basically, right? So this is specifically the numbers of hydrogens that are there in that particular compound. Well, 2 times 1 is 2 over 1 times 1, which is 1, and this is going to turn into kind of equivalent per liter, right? Because my mole of HCl cancels here and here, and what I've left over with is just something that we would call an equivalent, or a mole of H plus, and then this is liter. So 2 times 1 is 2 equivalents per liter, and that is known as normality. So another way that we can do dimensional analysis to solve normality in this type of case. All right, so let's try the other one, right? 2 moles of H2SO4 per 1 liter. That is molarity. Mole per liter, that's a 2, right? So in every mole of H2SO4, there are 2 hydrogens that are present. And we can call those equivalents. We can call them moles, but we can call them equivalents too, because we're only really talking about one part of the molecule, not the entire thing. So 2 times 2 is 4 over 1, so 4 equivalents per liter, and that is by definition the term normality. All right. Now, the reason that I'm introducing it this way is because, like I said before, normality can be used for anything. So I can calculate the normality of this compound, right? Well, some of you are probably going to think, well, how would I do this, right? That's not an acid, that's not a base. That's right. Because when we talk about acids, we traditionally automatically go to the H+. That's what we are focused on the most in the field of acid chemistry, right? If we're talking about a base, we automatically go to the OH group. How many OH groups do we have? So therefore, no one really has to write that down for you. Calculate the normality of H2SO4. We're automatically thinking about proton. Calculate the normality of sodium hydroxide. We're automatically thinking about the hydroxide piece. But calculate the normality of CaCl2, well, you might be confused. And this is where we have to be very specific, because we can calculate the normality of calcium or we can calculate the normality of the chlorine. And we have to be very specific on which one we want here, because it could be either or, right? It's not an acid, it's not a base. We might be focused on calcium, we might be focused on chlorine, we just don't know. So the problem has to tell us. All right, so let's calculate the normality of calcium and let's calculate the normality of chlorine on a 3 molar solution of this stuff, right? Okay, so for the normality of calcium, there's only one. There's one calcium for every molecule. So 3 times 1 is 3. So 3 normality for calcium. And I'm going to write that little bitty after the N, kind of like a subscript there at the bottom. And then I'll do the same thing for chlorine, right? Chlorine, there's 2 of them. So 3 times 2 is 6. So 6 normal Cl. Normality in regards to chlorine. So we basically do it just like we've done before. There's no difference with an acid or with a base or with a salt. We're still regarding the same type of thing. Now I can do this normality as well. So 3 molarity basically means 3 moles of CaCl2 over 1 liter. Mole per liter is molarity. So I'll bring in the next step of the dimensional analysis like we introduced before. Mole of CaCl2 on top, mole of CaCl2 at the bottom, and then I just want to go to mole of calcium only. And we can call that equivalence, right? For every 1 molecule, I get 1 equivalent of calcium. So for every 1, I get 1. So 3 times 1 is 3, divided by 1 is 3, so 3 normal Ca. I can do the same thing for the other one. 3 mole of CaCl2 over 1 liter. Bring in the dimensional analysis, mole of calcium chloride on top, mole of calcium chloride on the bottom. I want to go to mole of just chlorine only, right? Okay, for every 1 molecule, I get 2 equivalents. 2 moles of Cl minus, right? So molar equivalent can be either 1 in this case. So 3 times 2 is going to be 6. 6 normal when it concerns chlorine. So you can do it with a salt, you can do it with an acid, you can do it with a base, you can do it with anything you want, as long as you are in reference, clear reference to what normality is supposed to concern. Again, acids, we automatically default with H+. Bases, we automatically default with OH. If it doesn't have one of those, then we have to be a little bit more specific when normality is concerned. We can also talk about normality in terms of grams or milligrams, all right? And we want to think of these types of problems like molarity. So we can solve molarity if we have the starting amount of product, and we can calculate normality as long as we have the starting amount of product. It's just going to require an extra step. And quite honestly, it's going to be the easiest to go to molarity first and then convert that over to normality. All right, so let me kind of give you an example. Suppose that we take 200 grams of HCl, and, well, let me not choose HCl. Let's do H2SO4 here. 200 grams of H2SO4, and we put that into a 2.5 liter volumetric flask. And let's say the question wants to know what is the normality of the solution. Now, there's a couple of ways to do these problems, right? And I'm not going to show you every single way to do the problems. I'm going to show you what I think is the best way at this point to solve this type of problem. And the reason that I'm showing it to you this way is because it kind of sums up and reviews everything else that we've done so far up to this point. So why not reinforce it? Why introduce something completely new that we've not seen before to get us confused? Just use the tools that we already have to make this thing work. So 200 grams of H2SO4, so that's my given, and that's what I'm going to start with, 200 grams of H2SO4 over 1. And we know that grams can only go to mole in that roadmap that we've been talking about, right? So gram of sulfuric acid on top, gram of sulfuric acid on the bottom, and I need to go to mole of sulfuric acid. Okay, so I'm going to bring up my calculator here. And I'm going to take the formula weight of sulfuric acid. I need to know how many grams are in a mole. All right, so 1.01 times 2 plus sulfur 32.07 plus oxygen, which is 16 times 4. So there's 1, 2, 3, and 4. So 98.09 grams per every mole. So 98.09 per mole of H2SO4. All right, so this will give me moles. So I can take my grams now, 200, and I can divide by 98.09, and this will give me 2.04 moles of sulfuric acid. 2.04 moles of H2SO4, right? According to amount, that's how much I have. Well, I've taken that amount and I've divided it into 2.5 liters of solvent, right? So I'm going to take that, divide it by 2.5 liters, and this will give me mole per liter here, and we know that that is molarity. All right, so I'm going to take 2.04, and I'm going to divide that by 2.5, and I'm going to hit enter, and this gives me 0.82. I'm going to round it off. 0.82 molarity. We've done these types of problems already, right? We did these in the previous videos when we talked about molarity. We've done formula weights and converting grams to moles way back in the very first module when we went over those kind of introductory basic calculations. So what I've introduced here is nothing new. We've already talked about all of this. This was just a review. That's all that it was. So I've took the grams that they give me in the problem, and I took that amount, converted it to mole, divided it by volume, and this gave me molarity of my solution. Nothing new has been presented so far. Well, the only thing that we've got to do now is convert that molarity to a normality. And we now know how to do that because this is an acid and we're automatically looking at H2, right? So for every one molecule of H2SO4, I'll get 2 hydrogens from that, which basically means that I'm going to take my molarity and I'm going to double it. I'm going to times it by 2 because there's 2 protons for every one. So I'm going to take 0.82 and I'm going to multiply by 2, and that gives me the normality of the solution, and that's 1.63 H2SO4. That's all you got to do, folks. And that's what I'm going to tell you to do as of now, right? Whenever you get these types of problems that say, calculate this normality from this starting weight, I want you to take a look at these problems, and I want you to just automatically calculate molarity first. You should know how to do this. It's been talked about over and over and over. It's one of those staples that we have to be comfortable with in a lab, so why not keep doing it, right? So 0.82 molarity. That's the solution strength as far as molarity goes. And then if the question does ask for normality, just convert it over in the very last step. It's just one more step that you got to do. You just take a look at the proton, take a look at the OH group, take a look at whatever they want you to calculate for. It could be calcium like in above, it could be chlorine like above. Whatever the case is, convert that molarity to normality based on the number of those equivalents per molecule. All right? So from this point, I think that's all that I need to say about normality. I think that you have enough information now to go through and to tackle the next assignment. Hopefully that you'll not be confused between converting from one to another. Just remember, up here at the very top, I'm going to write it, and I'm going to write it in big red. Normality is always greater than or equal to molarity, right? We always said that hydrochloric acid, it's 1 to 1, so that's where they would be equal. Normality is equal to molarity. However, if it's not a 1 to 1, if there's 2, if there's 3, if there's 4, if there's 5, if there's 6 of them, who knows what we've got? Normality is always bigger because it's looking at the piece of, not the whole thing. And I know that sounds kind of weird and crazy, but normality will always be a bigger number, just like it was here, right? 0.82 for molarity. But we know that once this compound breaks down, it gives off 2 hydrogens for every 1 molecule, right? So because of that, normality gets bigger. That's always the general rule. So I think that if you write this up at the very top of your paper when you start working these problems and just keep that in mind, I think that will prevent you from getting confused. And if you look at your answers that you're providing and your normalities are smaller than the molarities, then you know that you're doing these problems backwards. So you need to go back, flip them around, and try to get a bigger number out of them. And I think that will help you quite a bit. All right, so good luck on the assignment. Again, normality based, pretty simple calculations. It's just a relationship. You might see 1 or 2 that are like this here at the very bottom, where they give you starting grams of stuff and want you to calculate molarity. So I've done one of those examples for you already, but it's just, what is the relationship between the 2 concentration units? And I think that you'll do okay. So good luck. Let me know if you've got any questions.